Termination of appropriate spot welding parameters. The determination of appropriate welding parameters for spot welding is a very complex issue, mostly based on years of experience. A small change of one parameter will affect all the other parameters. This, and the fact that the contact surface of the electrode is gradually increasing, makes it difficult to design a welding parameter table, which shows the optimum welding parameters for different circumstances. However, the following table shows target values for the welding parameters, which are perfect adapted to standard use applications. Spot welding parameters. Electrode force. The purpose of the electrode force is to squeeze the metal sheets to be joined together. This requires a large electrode force because else the weld quality will not be good enough. However, the force must not be too large as it might cause other problems. When the electrode force is increased, the heat energy will decrease. This means that the higher electrode force requires a higher weld current. When weld current becomes too high, spatter will occur between electrodes and sheets. This will cause the electrodes to get stuck to the sheet. An adequate target value for the electrode force is 90 N per mm2. One problem, though, is that the size of the contact surface will increase during welding. To keep the same conditions during the whole welding process, the electrode force needs to be gradually increased, as it is rather difficult to change the electrode force in the same rate as the electrodes are mushroomed. Usually an average value is chosen. Diameter of the electrode contact surface. One general criterion of resistance spot welding is that the weld shall have a nugget diameter of 5 T1/2, being the thickness of the steel sheet. Thus, a spot weld made in 2 sheets, each 1 mm in thickness, would generate a nugget 5 mm in diameter according to the 5*1/2 rule. Diameter of the electrode contact surface should be slightly larger than the nugget diameter. For example, spot welding 2 sheets of 1 mm thickness would require an electrode with a contact diameter of 6 mm. In practice, an electrode with a contact diameter of 6 mm is standard for sheet thickness of 0.5 to 1.25 mm. This contact diameter of 6 mm conforms to the ISO standard for new electrodes. Squeeze time. Squeeze time is the time interval between the initial application of the electrode force on the work and the first application of current. Squeeze time is necessary to delay the weld current until the electrode force has attained the desired level. Weld time. Weld time is the time during which welding current is applied to the metal sheets. The weld time is measured and adjusted in cycles of line voltage, as are all timing functions. One cycle is 1/50th of a second in a 50 Hz power system. When the weld time is taken from American literature, the number of cycles has to be reduced due to the higher frequency 60 Hz that is used in the USA, as the weld time is, more or less, related to what is required for the weld spot. It is difficult to give an exact value of the optimum weld time. For instance, weld time should be as short as possible. The weld current should give the best weld quality as possible. The weld parameters should be chosen to give as little wearing of the electrodes as possible. Often this means a short weld time. The weld time shall cause the nugget diameter to be big when welding thick sheets. The weld time might have to be adjusted to fit the welding equipment in case it does not fulfill the requirements for the weld current and the electrode force. This means that a longer weld time may be needed. The weld time shall cause the indentation due to the electrode to be as small as possible. This is achieved by using a short weld time. The weld time shall be adjusted to welding with automatic tip dressing, where the size of the electrode contact surface can be kept at a constant value. This means a shorter welding time. When welding sheets with a thickness greater than 2 mm, it might be appropriate to divide the weld time into a number of impulses to avoid the heat energy to increase. This method will give good-looking spot welds, but the strength of the weld might be poor. By multiplying the thickness of the sheet by 10, a good target value for the weld time can be reached. When welding 2 sheets with the thickness 1 mm each, an appropriate weld time is 10 periods 50 Hz. Hold time. Cooling time. Hold time is the time, after the welding, when the electrodes are still applied to the sheet to chill the weld. Considered from a welding technical point of view, the hold time is the most interesting welding parameter. Hold time is necessary to allow the weld nugget to solidify before releasing the welded parts. But it must not be too long, as this may cause the heat in the weld spot to spray it to the electrode and heat it. The electrode will then get more exposed to wear. Further, if the hold time is too long and the carbon content of the material is high, more than 0.1%, there is a risk the weld will become brittle. When welding galvanized carbon steel, a longer hold time is recommended. Weld current. The weld current is the current in the welding circuit during the making of a weld. The amount of weld current is controlled by 2 things. First, the setting of the transformer tap switch determines the maximum amount of weld current available. Second, the percent of current control determines the percent of the available current to be used for making the weld. Low percent current settings are not normally recommended, as this may impair the quality of the weld. Adjust the tap switch so that proper welding current can be obtained with the percent current set between 70 and 90%. The weld current should be kept as low as possible. When determining the current to be used, the current is gradually increased until weld spatter occurs between the metal sheets. This indicates that the correct weld current has been reached. Welding parameters for spot welding. Target values for settings of spot welding parameters: sheet thickness, T electrode force, F weld current, I weld time mmK cycles 0.63 plus 0.63 2.008 506 0.71 plus 0.71 2.128 757 0.80 plus 0.80 2.249 00080 0.90 plus 0.90 2.369 259 1.00 plus 1.00 2.509 510 1.12 plus 1.12 2.809 750 11 1.25 plus 1.25 3.15 10 000 13 1.40 plus 1.40 3.55 10 314 1.50 plus 1.50 3.65 10 450 15 1.60 plus 1.60 4.00 10 616 1.80 plus 1.80 4.50 10 918 2.00 plus 2.00 5.00 11 203 times 7 plus 2.24 plus 2.24 5.30 11 503 times 8 plus 2.50 plus 2.50 5.60 11 803 times 9 plus 3 2.80 plus 2.80 6.00 12 204 times 8 plus 2 3.00 plus 3.00 6.15 12 354 times 9 plus 2 3.15 plus 3.15 6.30 12 504 times 9 plus 2 parameters setting. In resistance welding, influence of the different welding parameters in the welding process. The principle of resistance welding is the Joule heating law, where the heat Q is generated depending on three basic factors as expressed in the following formula. Q equals I square RT, where I is the current passing through the metal combination, R is the resistance of the base metals and the contact interfaces, and T is the duration/time of the current flow. The principle seems simple. However, when it runs in an actual welding process, there are numerous parameters. Some researchers had identified more than 100 to influence the results of a resistance welding. In order to have a systematic understanding of the resistance welding technology, we have carried out a lot of experimental tests and summarized the most influential parameters into the following 8 types. 1. Welding current. The welding current is the most important parameter in resistance welding, which determines the heat generation by a power of square as shown in the formula. The size of the weld nugget increases rapidly with increasing welding current, but too high current will result in expulsions and electrode deteriorations. The figure below shows the typical types of the welding current applied in resistance welding, including the single-phase alternating current AC that is still the most used in production, the three-phase direct current DC, the condensator discharge CD, and the newly developed middle-frequency inverter DC. Usually the root mean square RMS values of the welding current are used in the machine parameter settings and the process controls. It is often the tedious job of the welding engineers to find the optimized welding current and time for each individual welding application. 2. Welding time. The heat generation is directly proportional to the welding time, due to the heat transfer from the weld zone to the base metals and to the electrodes, as well as the heat loss from the free surfaces to the surroundings. A minimum welding current as well as a minimum welding time will be needed to make a weld. If the welding current is too low, simply increasing the welding time alone will not produce a weld. When the welding current is high enough, the size of the weld nugget increases with increasing welding time until it reaches a size similar to the electrode tip contact area. If the welding time is prolonged, expulsion will occur, or in the worst cases the electrode may stick to the workpiece. 3. Welding force. The welding force influences the resistance welding process by its effect on the contact resistance at the interfaces and on the contact area due to deformation of materials. The workpieces must be compressed with a certain force at the weld zone to enable the passage of the current. If the welding force is too low, expulsion may occur immediately after starting the welding current due to fact that the contact resistance is too high, resulting in rapid heat generation. If the welding force is high, the contact area will be large, resulting in low current density and low contact resistance that will reduce heat generation and the size of weld nugget. In projection welding, the welding force causes the collapse of the projection in the workpiece, which changes the contact area and thereby the contact resistance and the current density. It further influences the heat development and the welding results. 4. Contact resistance. The contact resistance at the weld interface is the most influential parameter related to materials. It, however, has highly dynamic interaction with the process parameters. The figure below shows the measured contact resistance of mild steel at different temperatures and different pressures. It is noticed that the contact resistance generally decreases with increasing temperature but has a local ridge around 300 degrees Celsius, and it decreases almost proportionally with increasing pressure. All metals have rough surfaces in microscale. When the welding force increases, The contact pressure increases, thereby the real contact area at the interface increases due to deformation of the rough surface asperities. Therefore the contact resistance at the interface decreases, which reduces the heat generation and the size of weld nugget. On the metal surfaces, there are also oxides, water vapor, oil, dirt and other contaminants. When the temperature increases, some of the surface contaminants, mainly water and oil-based ones, will be burned off in the first couple of cycles, and the metals will also be softened at high temperatures. Thus the contact resistance generally decreases with increasing temperature, even though the contact resistance has most significant influence only in the first couple of cycles. It has a decisive influence on the heat distribution due to the initial heat generation and distribution. 5. Materials properties. Nearly all material properties change with temperature, which add to the dynamics of the resistance welding process. The resistivity of material influences the heat generation. The thermal conductivity and the heat capacity influence the heat transfer. In metals such as silver and copper with low resistivity and high thermal conductivity, little heat is generated even with high welding current and also quickly transferred away. They are rather difficult to weld with resistance welding. On the other hand, they can be good materials for electrodes. When dissimilar metals are welded, more heat will be generated in the metal with higher resistivity. This should be considered when designing the weld parts in projection welding and selecting the forms of the electrodes in spot welding. Hardness of material also influences the contact resistance. Harder metals with higher yield stress will result in higher contact resistance at the same welding force due to the rough surface asperities being more difficult to deform, resulting in a smaller real contact area. Electrode materials have also been used to influence the heat balance in resistance welding, especially for joining light and non-ferrous metals. 6. Surface coatings. Most surface coatings are applied for protection of corrosion or as a substrate for further surface treatment. These surface coatings often complicate the welding process. Special process parameter adjustments have to be made according to individual types of the surface coatings. Some surface coatings are introduced for facilitating the welding of difficult material combinations. These surface coatings are strategically selected to bring the heat balance to the weld interface. Most of the surface coatings will be squeezed out during welding. Some will remain at the weld interface as a braze metal. 7. Geometry and dimensions. The geometry and dimensions of the electrodes and workpieces are very important, since they influence the current density, distribution and thus the results of resistance welding. The geometry of electrodes in spot welding controls the current density and the resulting size of the weld nugget. Different thicknesses of metal sheets need different welding currents and other process parameter settings. The design of the local projection geometry of the workpieces is critical in projection welding, which should be considered together with the material properties, especially when joining dissimilar metals. In principle, the embossment or projection should be placed on the material with the lower resistivity in order to get a better heat balance at the weld interface. 8. Welding machine characteristics. The electrical and mechanical characteristics of the welding machine have a significant influence on resistance welding processes. The electrical characteristics include the dynamic reaction time of welding current and the magnetic/inductive losses due to the size of the welding window and the amount of magnetic materials in the throat. The upslope time of a welding machine can be very critical in micro-resistance welding, as the total welding time is often extremely short. The magnetic loss in spot welding is one of the important factors to consider in process controls. The mechanical characteristics include the speed and acceleration of the electrode follow-up as well as the stiffness of the loading frame/arms. If the follow-up of the electrode is too slow, expulsion may easily occur in projection welding. The figure below shows measured process parameters in a projection welding process, which include the dynamic curves of the welding current, the welding force and the displacement of the electrode, where the sharp movement corresponds to the collapse of the projection in the workpiece. Resistance spot welding tips. 1. Resistance welding with CDNAC is not recommended for aluminum, copper, or copper alloys. Use CDNAC for steel and stainless steel only. MFDC is suitable too. For more heat amperage output, use shorter tongs. 3. For units without a heat control, tong length can be used for a control. For instance, for thin metals where you want less heat, longer tongs can be used. 4. Keep in mind that longer tongs can bend, and you may lose pressure at the weld. 5. For the metals being welded, make sure there is no gap between the pieces. This will weaken the weld. 6. Keep the alignment of the tongs straight, so that the tips touch each other exactly. Also, maintain a proper pressure adjustment, not too much or too little pressure. 7. When you need one side of the weld to have good appearance, you can flatten machine the tip somewhat on that side. 8. Clean the tips on a regular basis, or you will lose output amperage. Dress the tips with a proper tip dresser.